In today's lesson, we are going to be looking at periodic and sinusoidal functions. So some of this would have looked at last year, primarily the sine wave, but you should be familiar with periodic functions, and we're going to be essentially the same thing with one small addition. We are also going to be looking at a cosine function. So just to kind of refresh ourselves, a periodic function has a pattern of y values that repeat at regular intervals. Each repeated section of a graph is called a cycle, and the length of a cycle, or the time it takes to complete one cycle, is called the period of the function. Right? So we have multiple cycles, and the length of one cycle is called a period of the function that we're looking at. Half the distance from the maximum to the minimum of this function is called the amplitude. So these are some kind of key terms, key things we're going to be looking at for periodic functions, and again, primarily sinusoidal functions. So looking at these examples here, these are all periodic functions. We can see a repetition of the values. So there's 1, there's 2, there's 3, there's 4, and so on. You can see it in here. There's 1, 2, 3. This one would be that. So there's 1, 2, and so on. And then here again, there's 1, there's 2, and so on and so on. So these are all examples of periodic functions. And the sinusoidal functions that we're going to be looking at, these are waves or repetitions of sine and cosine functions. So we're going to be looking primarily at the sine and cosine periodic functions. And this is an example of our cosine function. But before we get into looking more at them in depth, we want to make sure we understand what the key characteristics of each function is. And this is going to be important, especially when we start looking at the different characteristics or the different changes that we can make to our sine wave. So if I look at this, my maximum, the highest point in this case is going to be 1. We can see our highest point, which is 1. We can see our minimum is also -1. The lowest this goes is -1. Our amplitude is going to be 1, or half the distance from the maximum to the minimum. We can also say that it is the distance from the midline, which is the line that cuts it in half, the distance from the midline to our maximum or to our minimum. The period, the length of one cycle, is 360 degrees, or 360. We can see for repetitions, we start and end. It takes 360 degrees for one cycle. And there are key points that we want to be aware of, because again, it's going to help us understand how it's changing or how to draw our new sine wave or cosine wave. So we already have 2 points, our max and our min, and the points on the midline. Those are also going to be our nice key points. So we have 0, 0, we have 90 and 1, we have 180 and 0, we have 270 and -1, and we have 360 and 0. So again, we're going to be referring back to these key points when we're talking about transformations and how our sine wave and cosine wave can change. Looking at the cosine wave, it's very similar, right? We can see we have a maximum and a minimum. Both of these are 1 and -1. We can see our midline again, cutting it across. Hopefully, again, you can see the amplitude from the midline to the max and the min is 1, and the period as well. The period as well goes from 0 to 360. So again, we still have the same kind of characteristics. Maximum of 1, minimum of -1, amplitude of 1, period of 360 degrees. And our key points, a little bit different. Same idea though, we're looking for the maximum, the minimum, the midline points. So we see 0 and 1, 90 and 0, 180 and -1, and 270 and 0, and 360 and 1. So those are our key points. That's what those are the key points of the cosine wave. And hopefully you do at least recognize that the cosine wave and the sine wave are very similar. Right? They have very similar characteristics. The only difference are some of those key points. So let's look at a little bit of a warm-up. While riding a Ferris wheel, Carter's height above the ground in terms of time is given by the graph below. So we see our graph, time is on the x or t, and the height above the ground in feet is h or y. So based on this graph, what is the diameter of the wheel? So if we draw our wheel, just a crude, quick drawing, there's our Ferris wheel. What is the diameter of the wheel? What is this total distance? Well, if I look at the movement, the height goes from 10 is the lowest, and the highest, put that, the highest is 70, lowest is 10. So the diameter of the wheel has to be that entire distance, which is 60. So the diameter of the wheel is 60 feet. What is the period of the function graphed? So what is the period of this function? How long does it take for one cycle? So if I look, okay, we start here and I end here. I start at the bottom, I go to the top, and I come back down. That distance is my period, which in this case is 40 seconds. So the period of this function is 40 seconds. And the final part is, how high off the ground is the axle of the wheel? So the axle of the wheel is where it kind of joins right here. So how high off the ground is that? Well, we think the axle of the wheel is going to be in the middle of our wheel. We want to find our midline. What's the midline of our wheel? Well, if I look, right, if I know the entire diameter is 60, then the midline or the middle point should be 30 or half of 60. I can also look at my graph and see what line cuts this graph in half. And we can see that there. Right? That line is going to cut our graph in half. So that means the axle is 40 feet off the ground. Now, based off of all of that, the equation for this function is -30 cos 9t plus 40. So we want to know, how can these numbers help answer the question above? Where can I find these numbers? All in here, where can I find those numbers located in the graph, in that function? Well, looking at that, some do kind of stand out. Right, we do see 40. We see it twice though, so we want to be careful of which one is actually applying to the plus 40. We see a 30, we see a negative, we see a 9. Now, if you're not sure where these come from, the diameter of the wheel is going to be related to the 30. Right, 30 is half of 60. So 30 actually tells us our amplitude. And if we double that, that gives us our diameter. We do have a negative here as well. The negative tells us, and this one's a little bit different. This one we wouldn't be able to get from the graph without kind of knowing. The negative here tells us that it's flipped. If I look at my two base functions, right, if I go back up, cosine starts at the top or a maximum and then works its way down to a minimum. This starts at a minimum and works its way up. So this is the opposite, or flipped, from what we would expect. Now we're stuck with 9 and 40. 9 is multiplied by a value t, so that should be dealing something with time. In this case, the 9 is affecting time, and what the 9 tells us, well, the 9 tells us if I do 360 divided by 9, I get 40. So this is basically telling me how long the period is, or the 9 is actually telling me how many cycles there are per 360 degrees. So if I was to continue this cycle, I should already have 1, 2, 3, 4, 5 cycles. I should have 4 more by the time I reach 360 degrees. So this 9 can help us figure out the period and tell us how many cycles there are. In terms of answering the question, it would help us with the period part. Lastly, the plus 40. The plus 40 is going to tell us where our midline is. Right, so the plus 40, that is going to tell us where our midline is, or the middle of our function or of our wave. So it's going to tell us the midline or the middle. So we're going to look at each of these values in depth a little bit more to help us figure out or help us graph different sine and cosine functions. Again, you should have seen the sine wave last year. Cosine will be different. Cosine will be new because, again, it's a different base or different base function. So first, what we want to do is we want to sketch each of the following using the key characteristics. So we talked about this value here, this A value, or this value in front, telling us the amplitude. So that tells me where my max and my min are going to be, or the distance my max and min are going to be from the midline. There's no other changes, so for sine, I'm going to put my key points, and I'm just going to put the original one. So that's our original graph, or sine wave. The amplitude now, that's telling us that my amplitude is actually 2. So this is really only going to affect a couple points. It's going to affect these two here. And it's going to ensure that my amplitude, or my graph, now goes up to 2 and down to 2 from the midline. So my sine wave is actually going to look like that. Maybe a little bit off center. So my amplitude is 2, that has been changed. For B, -3 cos x, again, the -3 tells us the amplitude. And from the previous one, it tells us what the distance from the midline to the height should be, as well as the negative there is telling us that it should be flipped. So I'm going to put down my original graph, because it is always helpful to know the original and then change it to effect based off of these new values. So the -3 means 1, it's flipped. So instead of it being at 1 and then 0 and then 180, 0 and 1, it's going to flip. So essentially, it's going to look now like this. So now we're going up and coming down instead of going down and coming up. So that's the negative taken into account. 3 tells us that the amplitude should be 3. So my max and min should be 3 units from the midline. If it helps, you can always draw the midline in. In this case, it's going to be right along the x. And my max and min are these 3 points. So they should all be 3 units from the midline. So not at 1, but at -3 and +3. So now when I connect them and draw my cosine wave, I do get an amplitude that is 3. So how does this A value, this leading coefficient, affect these two functions? Well, A determines the amplitude, which is the distance from the midline to the max or the midline to the minimum. Keep in mind as well, if it is negative, it is flipped. So negative means that it's flipped. It's the opposite of our base function. It's going in the opposite direction. And I'm going to add a little small thing. basically, essentially, what we're doing to the individual values, we multiply the y value by a. And we'll come back to these little changes at the very end when we look at some more difficult ones. So C and D are again looking at two different changes, or two kind of a new variable, so to speak. So sine x minus 1. We talked about previously, this minus 1 tells us our midline. So that means my midline for this sine function is going to be here. If I go back to my base function, the base sine wave, my starting point is on the midline at 0 when x is 0. At 90, I'm at my maximum, which in this case is going to be 1, up because I can see my initial value here. I don't see anything there, so there's an invisible 1, which tells me my amplitude has to be 1. So the distance from there to there has to be 1. At 180, I come back to my midline. At 270, I go to my minimum, so 1 away from the midline in the negative direction. And then I come back up to 360. I can connect the dots or connect my points, and there is my new sine function. For D, 2 cos x plus 1. So we have two things to consider now. One, the plus 1, which is telling us our midline, and 2, which is telling us our amplitude. So I'm going to draw in my midline first. So that's going to help me kind of figure out my points. So my midline should be at positive 1. So the middle part of my graph needs to be at positive 1. Nothing else has changed except for the amplitude. And if we go back to our base function for cosine, we do start at our maximum. So that means my maximum needs to be 2 units away or above the midline. So 2 units above 1 is 3. Then going through my key points, at 90, I'm at my midline. At 180, I'm at my minimum, so 2 below because of my amplitude, or my new amplitude. 270, I'm at the midline. 360, I'm at my maximum, or 2 above. If I draw my points in, or if I draw my line in and I connect them and I see that my amplitude is not 2, or 1, it is 2, and we can see that as well. So what effect does this D value have on our sine and cosine wave? Well, this gives us a vertical shift up if it's positive, or down if it's negative. You can also think about it telling us our midline of our graph. And one key characteristic of what it's going to do, and again, we'll come back to all of these, we add or subtract it to the y value. And we'll come back to those, to these terms that we're putting in purple at the very end, like I said, when we deal with a complex equation or transformation. So there are 4 here that I would like you to try on your own. These are only dealing with the D value and the A value, so you only have to worry about changing the amplitude and shifting it up or down, or potentially flipping it. So try these 4 on your own, and then I recommend pausing the video, and we'll come back with the answer. So again, pause the video and see if you can draw these functions on your own. So coming back to our 4 examples, this is what we should have. Right, so if we look at the first one, 3 sine x plus 1. The plus 1 means our midline is at positive 1. The 3 means our amplitude is 3. So the sine wave starts on the midline, or starts at 0. At 90, we're at our maximum, or up 3. 180, we're back at our midline. And 270, we're at our minimum, or down 3 from the midline, and then back up to our midline for 360. Right, So all of these, we're keeping it at 0, 90, 180, 270, 360 because we're only affecting the vertical kind of transformations. We're stretching it up and down, or we're shifting it up and down. So nothing's changing in terms of left and right. So that's why I'm kind of putting these kind of points down, or these key points down very easily, because I know that nothing is affecting the wave horizontally. For B, again, midline of +1. The amplitude is still 1, because we see an invisible 1 here, but it is negative, so we flip it. So that means instead of our cosine wave starting at the maximum and going to the minimum, we're starting at the minimum and working our way up to the maximum. So the maximum in this case is going to be 1 away from the midline, or in this case, the minimum is going to be 1 below the midline. 90 is at our midline. 180 is at our maximum, and back to our midline, and then to our minimum. For C, similar idea, almost the exact same thing. Graphically, it looks the exact same, and it looks like the values are in the same spot. Just keep in mind what the scale of our graph is, especially the y values, because that will basically help determine what the shape is. So even though this is a different function, it does look the same on our graph based on what our values or the scales are. But again, our midline is at 2. It is flipped, so we're starting at a minimum instead of a maximum, and our amplitude is 2. So that max and min should be 2 spots or 2 units away from the midline. For D, -2 sine x minus 1. Again, it tells us our midline is at -1 and our amplitude is 2. The negative tells us it's flipped. So that means instead of our sine wave starting at the midline and then going up, we start at our midline and then go down. So we start at -1, we go down to -3 at 90, because again, our amplitude is 2, so we should be 2 away or 2 down from our midline. Back up to the midline at 180, back up to our maximum, then back to the midline. So again, it is very helpful to understand the base functions to allow us to kind of visualize what these changes are. Now, the next one is going to get trickier. These transformations will be trickier because now we're going to deal with some horizontal changes. So let's sketch these functions using the key characteristics. So using kind of what we know. So 2 sine 2x. So we already know the 2 tells us the amplitude. And we mentioned before that this 2 here, that tells us, or that helps us to figure out how many cycles or that there are in 360 degrees, or it helps us figure out the period. Right? In the previous example, it was 9 and our cycle was 40, or our period was 40, because we had 9 cycles. Here we have 2, which means we have 2 cycles. So to figure out the period, 360 divided by 2 is 180. So what that number means is that my entire sine wave should fit in 180 degrees. That also means that I will have 2 of them from between 0 and 360. So how we can figure this out? Well, first, we know where we're going to start. We're always going to start here because that's not changing. Now, I'm going to draw the base function, right? So 0, or I'll include the amplitude because I know the amplitude needs to, I know what that is. I've dealt with that before. I'm going to draw the base function here to help us sketch this and visualize it. So here is my function. What the 1, 2 attached to the x is telling us is that I need to have 2 of these inside 360 degrees. So that means this entire wave needs to shrink to fit between 0 and 180. Now, if I look at this, what happened to my values? Well, the max and the min didn't change, right? Our amplitude didn't change. Right? These are still 2, which we want. My midline didn't change. That's still 0. So what happened? Well, the x values changed, right? This maximum used to be at 90, but now it's at 45. This midline here used to be at 180, now it's at 90. This used to be at 270, now it's at 135. And this used to be at 360, now it's at 180. So all of my values, all of my x values have been basically divided in two. They've been cut in half because we've compressed our graph to fit into half the distance, so to speak. I can continue the pattern as well to fill in my second wave so I can see the same thing. And again, if that part is a little bit confusing, we'll talk a little bit more about what we want to do to find these new values. But let's look at B. We still have our amplitude. And the 1/2, this is telling us how many cycles there are per 360 degrees. So if I do 360 divided by 1/2, or 0.5, I get 720. That tells us that I have, or the length of one cycle, or the period, is 720 degrees. I only see 360 degrees, so I should only see half of my cosine wave. So let's draw the original cosine wave and we'll talk about adjusting it. So I know amplitude of 2 means I start at 2, then back to my midline, down to 2, up to my midline, and back up to 2, my maximum. So this is what my cosine wave should look like. But it says that I have half of my sine wave, or half of my cycle, in 360 degrees. So let's extend this. We'll stretch this out. There. So that is what my one cycle of my sine wave should look like. It's been stretched, so now it covers 720 degrees, and we only see half of it in 360 degrees. So that fits. But what happened to my values? Well, the amplitude didn't change. Right? That's still 2. My midline didn't change. That's still at 0. What happened to the x values? Similar to the last one. Well, this point here, right, this midline here, that point should be at 90. It's now at 180. This point here should be at 180. Now it's at 360. So all of my x values doubled, which makes sense because we've stretched our function, we've stretched our sine wave so that each cycle takes double the amount of time. So how does this k value, the one that's attached to the x, how does that affect our function? Well, it tells us it tells us how many cycles per 360 degrees. It tells us that's how many cycles it tells us. We can also figure out the period by doing p equals 360 divided by k. So that will tell us how long one cycle should be. So again, it helps us visualize it if we need to. And again, like I said, in purple, I'm going to be putting something down. Essentially, we divide the x values by k. And we're going to come back to these purple values again shortly. So let's go through and try to sketch these. So again, these are going to be some practice. So I want you to try to go through and do these on your own. I'll walk through the first one with you so you get a general idea. Right, so we have two values. This value tells us our midline. So I'm going to put that one down first. We don't have any change in our amplitude because we don't have an A value. But this value here, this 3, This tells me that there are 3 cycles per 100 or per 360 degrees. So if I do 360 divided by 3, I get 120. So that means every 120 degrees, I should have 1 cycle for my cosine wave. Now, if it helps to visualize, we can take our cosine wave, the original one. Get rid of this midline just for now. If it helps to visualize, I can take this cosine wave and I want to fit it all the way within 120 degrees. Oops. A little bit too much. There. So let's take a look at the x values. What has happened? Well, it used to be at 90 for the midline here. Now it's at 30. My minimum used to be at 180. Now it's at 60. Back at the midline used to be at 270. Now it's at 90. My other maximum used to be at 360. Now it's at 120. So all of the x values has been divided by 3, which makes sense because I've basically combined, or I've put 3 cycles into 360 when there used to be 1. So they're only allowed to take up a third of the space they used to. So all of the x values have been divided by 3 from my original base function. Now to find out all the other points, I'm just going to go through and just kind of repeat them, right? Because it is that sine wave. So it is easy to kind of draw the other ones once we have the first one done. And we can see that the amplitude is still the same. We do have, oh, we didn't put our midline. My mistake. So we do actually have to do one more thing. I was thinking the midline was at 0. It's not, it's actually at 1. So the nice thing about this, at least on what I'm using, I can just shift everything up. And that is what it should look like, because again, my midline is at 1 and not 0 like I originally had done it. So go through the next 3, take into account what the other values are that we already talked about, and keep in mind for these ones, you are going to have to adjust the horizontal distance, right? You're going to either be compressing or stretching horizontally your sine or cosine wave. So pause the video and try to do the next 3 on your own. So coming back to these 3 graphs, this is what we should have. Just look at all of them, and let's go into number 2. So looking at number 2, right, we see that our amplitude is a half. So from the midline to our maximum should be half, and same from the midline to the minimum. And our k value is a half. This means that basically in 360 degrees, we will see half of our sine wave or our function. That also tells us that the period for an entire function is 720 degrees. So this means I am stretching my graph, so I need to double the distances that they originally are. The starting point is still the same, that's not going to change. Now my maximum used to be at 90. Now, because I had to double it, it's now at 180. My other midline, or when I came back to my midline, used to be at 360, or sorry, at 180, but I've had to double it, and now it's at 360 degrees. So I only see half of my sine function or sine wave here. I only see it going up to the maximum and coming back, which again makes sense because the other half will cover the minimum part, and by the time I make it to the end, I will have completed 1 cycle and got 720 degrees. For 3, amplitude of 2, a midline of -1, and the 2 for the k value tells us that our period is 180 degrees, or that there are 2 cycles per 360. So in this case, my cosine wave, I'm starting 2 units above the midline. So if the midline is at -1, I'm starting at 1. Now, because I have to compress everything into 180 degrees, or half the distance that I had, my x values all have to be divided by 2. So instead of being at the midline at 90, I'm at the midline now at 45 here. My minimum, instead of being at 180, is at 90. Oops. Not mean to do that. My next midline, instead of being at 270, is 135. And then finally, my final value, instead of being at 360, it's at 180. The amplitude is still 2. I can see that. And if I repeat that pattern, I will end up with 2 cycles in the 360 degrees, which the K value tells me. Finally, for the last one, sine wave, an amplitude of 2 and a K value of 1/4, meaning I will see 1/4 of my sine wave in 360 degrees, or it takes 1,440 degrees for 1 cycle. So here we can see I still start at my midline. That hasn't changed, right? We're not changing the midline or where we start yet. That'll be the next one. And my maximum that we see here is usually, keep on erasing the wrong thing. My maximum is usually over here at 90 and 2. However, because my sine wave now takes up 4 times the amount of space, or I only see 1/4 of it in 360, I have to divide all of my x values by 1/4 or multiply them by 4, which means this value here goes from 90 over to 360, because 90 divided by 1/4, or 90 times 4, gives us 360 degrees. So I only see 2 points of my sine wave over here. And that is those 3 examples, looking at the A, the K, and the D value. We have one last value to look at. And that one we didn't quite look at, or we didn't see in the Ferris wheel example. But this value is our C value. So if I look at my examples, I have 2, which is my amplitude still. And I have -60. I don't really know what this means. We may remember from last year, but the -60 is actually telling us to shift right 60 degrees. So I'm going to go through and just draw my base function with the amplitude, because again, we should be fairly confident with that. So for the sine wave, should look something like this with an amplitude of 2. Right, I still have my amplitude of 2 from the midline to the max and the min. But now this -60 is telling us that I need to take, I guess I'll draw the wave. It's telling us that we need to take this entire wave and shift it over 60. Which we have here. So now all of my x values have shifted over 60 degrees. So I'm going to get rid of that last one just because it's not on the graph. I'm going to redraw in my points. You can see that we've gone over 60 degrees. So every point has shifted over 60. If I look at the next one, cosine 2x plus 30, this one is basically telling us 2 things. One, it's telling us that we're going to be compressing it, and it's telling us that we're shifting everything to the right, or to the left 30. So this is our K value. So this tells us 360 divided by 2 equals 180. So everything is getting compressed into half the amount of space. And this value is telling us now left 30. So we're going to take it one step at a time. Let's deal with the compression first. So my normal cosine wave start at 0 and 1, 90 and 0, 180 and negative 1, and so on. So that is our normal wave. Now, what the 2 is telling us is that we need to shrink all of this to fit in half the distance. Or in other words, I'm dividing all of my x values by 2 because they have half the distance that they're allowed to cover. So now I've taken into account the k value. The next thing I now have to do is shift everything over to the right, 30. So that is what my new sine function should look like. I can still see that I have a distance of 180, or I'll put it at the bottom, or a period of 180. And I've now shifted over to the left 30 degrees. I'm actually just going to go back and quickly just draw on those points just because they're not too accurate. Here, here. Draw that a little bit better. Oops. It's not the easiest thing drawing curves. So that's one function. Then the next one. Oh nope, it's too off. Drawn it too big. There, so that's nope. There we go. That's where the values are. So I've drawn the one wave. I'm going to draw the next one in as well because I can kind of repeat the pattern. Or essentially, instead of it being 90 over from everything, it's going to be 45 for my gaps instead. And it's over 30. So if it is confusing to draw some of the other values just because we haven't, we don't really know what the key values are beyond 360 degrees, as long as you have one wave, that is fine. So what effect does C have on our functions? Well, it tells us to shift left or right. And the key thing is it's going to be opposite of what it appears. Because our base function, which we can see here, our base function here tells us that we're all automatically subtracting C. So if it's a positive value, usually indicating moving to the right, by subtracting a positive, I'm actually appears as subtraction. If I have a negative C value indicating that I move to the left, in the equation, minus a negative appears as a positive. So that's why we do the opposite of what we see. And then finally, just a little bit in brackets, we add or subtract from x. So if we go back and look at all of those examples, I did have some values or some descriptions in purple. So what all of that means, that is going to help us when it becomes very complicated like this. Right? We have 4 transformations to deal with. So what I was writing down in purple is basically what we call mapping notation. So if I have a base function x and y, and I transform it, or transformation notation, I'm not sure the exact terminology, but I believe it's mapping notation. Everything that's affecting the x value, we take our x value, we divide it by k, and then we add our c value. For the y, we multiply it by a, and then we add our d value, whatever that happens to be. So this is going to be what we do for our mapping notation. I'm just going to simplify or write it down a little bit smaller. And essentially we apply the a and d value, or apply a and d to the y value, and we apply the c, or the k and c value, to the x value. So what does that look like? Well, let's go through and look. If I look at my two examples here, 2 sine 2x minus 30 plus 1, I want to go through and at least figure out what these values are telling us. So the 2 tells us the amplitude. This 1 tells us the midline. This 2 here tells us that 360 divided by 2 equals 180, or my entire cycle has a period of 180. And then lastly, this minus 30 tells us that we are actually moving to the right 30 degrees, opposite of what we see. So how can that help us, those values help us sketch? We could go through and apply each one individually, one at a time, and see how it, and then get our final transformation. We may want to do it all at once. So what that means, I need to know my base function. 0, 0, 91, 180, 0, 270, negative 1, and 360, 0. That's my original function. The transformed function now is going to be, using this mapping notation, x divided by k, so x divided by 2 plus 30. Again, opposite of what we see for that c value. So plus, let me make it a little bit bigger. X divided by 2 plus 30. And then our y value is going to be 2 times y, because the a value, plus 1. So now all I'm going to do is go through and apply these changes to each of the x values from those key points. So now, 0 divided by 2 is 0, plus 30 is 30. 2 times y, or 2 times 0 is 0, plus 1 is 1. 90 divided by 2 is 45, plus 30 is 75. 2 times 1 is 1, plus 1 is 2. 180 divided by 2 is 90, plus 30 is 120. 0 times 2 is 0, plus 1 is 1. 270 divided by 2 is 135, plus 30 is 165. Negative 1 times 2 is negative 2, plus 1 is negative 1. And 360 divided by 2 is 180, plus 30 is 210. 0 times 2 is 0, plus 1 is 1. So these values here, these are the new values of my new transformed sine wave. So let's go and plot them. So 30 and 1, 75 and 2, I think I made a mistake. Oh, not 2, this should be 3, sorry. Because 1 times 2 is 2, plus 1 is 3. I knew something seemed off a bit. Then 120 and 1, 165 and negative 1, and 210 and 1. So this is my sine wave based off of my key points. And if I go through and look at this, I can see my midline, which is positive 1. I can see the amplitude, which is 2. I can see there's a shift to the right 30. And I see a period of 180 degrees. So that's an easy way to go through and do all of those transformations at once rather than trying to worry about visualizing it in your head and moving things around. Sometimes it helps just having the formula and plugging values in. So let's try it with the next one. Same idea. Let's go through. We have our amplitude. I'm just going to write down what our values are. So we have our A, we have our K value, we have our C value, and we have our D value. So for this one, we're going to focus on the cosine coordinates. So the original cosine coordinates, x and y, we had 0 and 1. We had 90 and 0. We had 180 and -1. We had 270 and 0. And we had 360 and 1. So again, that is all just right from the key points that we talked about at the very beginning. Now, if we plug this in to our mapping notation, x is going to be divided by k, so x divided by 0.5 plus c, or 90. And then y is going to be multiplied by -1. So you can put the -1 or just leave it as -y, and then plus 2. So now let's go through and apply these changes to each coordinate. So for the first one, 0 divided by half is 0, plus 90 is 90. 1 times -1 is -1, plus 2 is 1. 90 divided by a half is 180, plus 90 is 270. 0 times -1 is 0, plus 2 is 2. 180 divided by a half is 360, plus 90 is 450. So 450, -1 times -1 is +1, plus 2 is 3. 270 divided by a half, or 270 times 2, is 540, plus 90 is 630. 0 we've already done before, which gives us 2. And 360 times 2 is 720, plus 90 is 810. And we've already done the calculation for 1 before, which gives us +1. Wait a second. Yep. So some of these values might look different, but we have to keep in mind we have shifted things over. So it's going to be maybe not in the same place that we normally see it. So let's just at least graph what we're able to. So 90 and 1, 270 and 2. And realistically, that's it. That's all we're able to graph right now. Now, if we think about our cosine wave, we know it's flipped, so it should be going, instead of like this, sorry, like this, it should be going like that. So we can at least use that to kind of help us kind of draw our points. And we know that we're kind of going from a minimum here to a maximum that we're going to get at 450. So we can kind of draw that part out. We can see a little bit of our midline. We can still see the amplitude of 1. We can see a shift of 90 to the right. We don't really see the full period. We don't see the 360 degrees because, well, you kind of could. We could argue that we see half of it, but we don't see the full period. So when we get really complicated equations, it's really helpful if we use this mapping notation, because in that way it kind of takes out some of that guesswork. Let me just write this closer. It takes out some of that guesswork or that difficulty if we're trying to visualize things. x over y becomes again x divided by k plus c over ay plus d. So again, if anything, this is the key thing that we really want to be focusing on. You can use this in any form or any different type of transformation. Keep in mind, if there is no value there, we have to be aware of whether it's a 0 or a 1. Anytime we're multiplying, so basically your a and your k, if we don't see a value, we assume it's 1. Your c and your d, if we don't see a value, we assume it's 0. And that is all of our transformations of our sinusoidal functions. So again, some of it should be review from previous years. The new part should be cosine law, and maybe this mapping notation, maybe this might be new. And as well as I think some of the horizontal transformations. But make sure you're comfortable being able to go from the equation to the visual or the graphical representation.